Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video, we will talk about Newton's laws in engineering fundamentals. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comments section or reach out to me via the email provided in my profile. Newton's laws of motion. Sir Isaac Newton was one of the most influential scientists in history, making important contributions to both mathematics and physics. In 1666, at the young age of 23, he developed the theory of gravitation. Later, in 1686, he published his groundbreaking book Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, where he introduced his three laws of motion. By formulating these laws, Newton completely transformed science. Along with Kepler's laws of planetary motion, they explained why planets travel in elliptical orbits instead of perfect circles. These laws remain the foundation of mechanics, aerodynamics, and modern engineering. The three laws of motion overview. 1. First law. An object at rest remains at rest, and an object in motion remains in motion at constant speed and in a straight line, unless acted on by an unbalanced force. 2. Second law. The acceleration of an object depends on the mass of the object and the force applied to it. 3. Third law. Whenever one object exerts a force on another, the second object exerts an equal and opposite force on the first. Let's go step by step and learn about each of these laws. Newton's first law, inertia. Newton's first law, also called the law of inertia, states that every object will remain at rest, or in uniform motion in a straight line, unless compelled to change its state by the action of an external force. This resistance to changes in motion is called inertia. If the net force acting on an object is zero, its velocity will not change. Objects with more mass have greater inertia and are harder to accelerate or decelerate. Examples of inertia in aerodynamics. The motion of an airplane when a pilot changes the throttle setting of an engine. A ball falling down through the atmosphere until drag balances gravity. A model rocket continuing upward after launch, even when thrust stops. A kite resisting changes when the wind shifts direction. Let's go step by step. The motion of an airplane when a pilot changes the throttle setting of an engine. An aircraft in flight is an excellent example of Newton's first law of motion. There are four major forces acting on an aircraft: lift, weight, thrust, and drag. If we focus on the motion of an aircraft flying at a constant altitude, we can simplify the scenario by neglecting lift and weight. In this case, a cruising aircraft flies at a constant airspeed because the thrust exactly balances the drag. This illustrates the first part of Newton's first law. When there is no net force on an object, it continues to travel at a constant velocity in a straight line. Now, if the pilot changes the engine thrust, the balance between thrust and drag is disrupted. For example, if the thrust is increased, the aircraft accelerates and its velocity rises. This demonstrates the second part of Newton's first law. An external force changes the velocity of an object. As the aircraft speeds up, the drag also increases because drag depends on the square of the velocity. Eventually, the drag grows to match the new thrust level, at which point the forces are balanced again. The aircraft then continues to fly at a new constant velocity, which is higher than the initial speed. Once more, we return to the first part of the law, constant velocity when net forces are zero. It is important to note that in this simplified example, we are considering only horizontal motion, ignoring any effects of thrust on weight or lift. In a real aircraft, increasing the throttle increases fuel usage, slightly reducing weight, and the increase in velocity affects both lift and drag. These factors also influence vertical motion. However, to clearly understand Newton's laws, we are neglecting these complexities here. This example also highlights the role of engine thrust. Thrust serves two key purposes: to accelerate the aircraft and to balance drag during cruising. We often focus only on the first purpose, acceleration. High thrust is crucial for fighter planes, where rapid acceleration and maneuverability are needed. On the other hand, jet airliners spend most of their flight in cruise mode, where thrust primarily balances drag. In this scenario, engine efficiency, low fuel consumption becomes more important. Depending on an aircraft's mission, engines are designed to prioritize either high thrust or high efficiency. A ball falling down through the atmosphere until drag balances gravity. An object falling through the atmosphere is another clear example of Newton's first law of motion. Just before release, the object's velocity is zero, it is at rest. At this moment, the weight force acting on the object is balanced by the tension force in the rope. With no net force acting on the object, it would remain at rest indefinitely. When the rope is cut, the tension force is removed, and the object is now subjected to a single force, the gravitational attraction of the Earth. Since there is initially no air resistance, the object begins to free fall and accelerate. As the object's velocity increases, it encounters air resistance or drag, which opposes the motion. The magnitude of the drag depends on the square of the velocity. The drag continues to increase until it matches the weight of the object. At this point, the net external force is zero, the acceleration stops, and the object falls at a constant terminal velocity. The exact value of this terminal velocity depends on several factors: the weight of the object, its drag coefficient, the density of the air, and the size of the object. A model rocket continuing upward after launch, even when thrust stops. A model rocket being launched into the atmosphere is another excellent example of Newton's first law. Before ignition, the rocket is at rest on the launch pad. Its velocity is zero, and there are no unbalanced forces acting on it. The rocket will remain at rest indefinitely until an external force acts upon it. When the engine ignites, it produces thrust, which is an external force that acts on the rocket. According to Newton's first law, this force causes the rocket to accelerate upward. The initial motion is directly caused by the unbalanced force of the thrust overcoming the rocket's weight and any small frictional forces from the launch guide. As the rocket rises, it encounters air resistance, drag, which opposes its motion. The drag force increases with the square of the rocket's velocity, gradually reducing its acceleration. Eventually, when the engine stops producing thrust, the net upward force disappears and gravity becomes the dominant force. At this point, the rocket slows down, stops momentarily at its peak, and then begins to fall back to the ground. This example demonstrates both parts of Newton's first law. 1. At rest, the rocket remains stationary until acted on by thrust. 2. In motion, Once the thrust is applied, the rocket accelerates, and its velocity changes until the forces acting on it balance or change again. A kite resisting changes when the wind shifts direction. A kite flying through the air is another clear example of Newton's first law of motion. The main forces acting on a kite in flight are its weight, the aerodynamic lift and drag, and the tension in the control line. When the kite is in stable flight, these forces are balanced and the kite maintains a fixed altitude. Its vertical velocity is zero because there is no net force acting in the vertical direction. If the wind speed increases slightly, the lift and drag forces increase, since aerodynamic forces depend on the square of the velocity. The forces on the kite are no longer balanced, resulting in a net vertical force. The kite moves upward because the lift now exceeds the weight and the vertical component of the tension in the control line. As the kite climbs, the tension in the control line increases due to the greater lift and drag. The tension is a vector quantity, so it can be resolved into horizontal and vertical components. The vertical component increases as the tension increases, gradually reducing the net upward force. Eventually, a new balance is reached, where the lift equals the weight plus the vertical pull from the line. The kite then flies steadily at a slightly higher altitude. If the wind decreases, the lift, drag, and vertical pull all decrease as well. The kite adjusts downward and establishes a new stable flight condition at a lower altitude. Newton's second law, force and acceleration. Newton's second law defines the relationship between force, mass, and acceleration. In its most general form, it states that the force applied to an object equals the change in momentum divided by the change in time. Force equals the product of the mass at the later point in time multiplied by the velocity at the later point in time, minus the product of the mass at the initial point in time multiplied by the velocity at the initial point in time, all divided by the change in time. Force is the external push or pull on an object. Mass is the amount of matter in the object. Velocity is the speed and direction of motion. Time is the duration over which the force acts. This means that force is equal to the change in momentum, mass multiplied by velocity, over time. For many practical problems, such as airplanes, cars, or balls, we can assume the mass remains constant. In that case, the equation simplifies to the familiar form. Force equals mass multiplied by acceleration. Acceleration is the change in velocity per unit of time. This tells us that a larger force causes a larger acceleration. Heavier objects accelerate less than lighter ones if the same force is applied. If no force acts, acceleration is zero and the object continues at constant velocity. Because force, velocity, acceleration, and momentum all have both magnitude and direction, they are vector quantities. This means the law applies in 3 dimensions simultaneously: up, down, left, right, forward, backward. An important fact to remember is that a force will cause a change in velocity, and conversely, a change in velocity can generate a force. This relationship works in both directions. The velocity, force, acceleration, and momentum all have both magnitude and direction, which makes them vector quantities. This means they are not just numbers, they have a specific direction in space. The equations of motion we use are therefore vector equations, and they can be applied to each component of motion independently, whether in the forward-backward, left-right, or up-down directions. For example, the motion of an aircraft can be analyzed using Newton's second law. The forces acting on the aircraft, aerodynamic lift and drag, weight, and engine thrust determine its acceleration and velocity. By calculating the net force in each direction, we can predict how the aircraft will move and respond to changes in thrust or drag. Examples of force in aerodynamics. An aircraft accelerates when engine thrust is greater than drag. An airplane climbs when lift is greater than weight. A jet's acceleration depends on thrust produced compared to its mass. Newton's third law, action and reaction. Newton's third law states, for every action, there is an equal and opposite reaction. This means forces always come in pairs. If object A exerts a force on object B, then object B exerts an equal force back on object A in the opposite direction. For aircraft, the principle of action and reaction is particularly important. It helps to explain how lift is generated by an airfoil. In this case, the airfoil pushes the air downward, the action, and in response, the wing is pushed upward, the reaction. A similar principle applies to a spinning ball. As the ball moves through the air, it deflects the air to one side, the action, and the ball moves in the opposite direction, as a result, the reaction. Jet engines also rely on this principle to produce thrust. The engine expels hot exhaust gases out of the back, the action, and in response, a thrusting force pushes the aircraft forward, the reaction. In all these examples, forces always occur in pairs. Every action produces an equal and opposite reaction, and this fundamental concept explains much of the motion we observe in both aerodynamics and everyday life. Examples of action and reaction in aerodynamics. A wing deflects air downward. In reaction, the air pushes the wing upward, lift. A spinning ball deflects air to one side, and the ball curves in the opposite direction, Magnus effect. And finally, what we have already discussed, a jet engine expels exhaust gases backward, and the aircraft is pushed forward with equal thrust. Quick review of Newton's laws. 1. First law, inertia. Objects resist changes in their motion. 2. Second law, force. Force equals mass times acceleration. 3. Third law, action and reaction. Every action has an equal and opposite reaction. These three simple but powerful principles form the basis of classical mechanics and continue to guide engineering, physics, and aerodynamics today. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. Which of the following best describes Newton's first law of motion? The correct answer is an object at rest remains at rest, and an object in motion remains in motion unless acted on by an unbalanced force. Question 2. When a cruising aircraft flies at constant speed, which forces are balanced? The correct answer is thrust and drag. Question 3. A model rocket continues to rise after its engine stops because the correct answer is Newton's first law. The rocket maintains its motion until another force acts. Question 4. Newton's third law explains how a jet engine produces thrust by stating the correct answer is for every action, there is an equal and opposite reaction. Question 5. Terminal velocity of a falling object is reached when the correct answer is the drag force equals the weight of the object. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with Aerospace Engineering, Avionics and Aerospace Systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about fundamental conservation laws, mass, momentum, and energy. See you in the next video. Bye.